Every call to a large language model costs you tokens and latency. If your users ask the same thing in slightly different words, you pay full price every single time. A naive string cache won't help, because nobody phrases a question identically twice. In this video, we build a semantic cache for Azure OpenAI in Python. We use embeddings to recognize when two prompts mean the same thing, serve a stored answer in milliseconds, and only hit the model on a genuine miss. We'll cover the mental model, the lookup mechanism, the three settings that actually matter, and the gotchas that bite you in production. A traditional cache is a hash map. The key is the literal prompt, and you get a hit only on a byte-for-byte match. A semantic cache replaces equality with similarity. Instead of hashing the text, you convert each prompt into a vector embedding, a list of floating point numbers that captures meaning. Two prompts that mean roughly the same thing land close together in that vector space. So the lookup becomes find the nearest stored vector, and if it's close enough, return its cached answer. The trade-off is obvious. Exact caching is precise but brittle. Semantic caching is forgiving but probabilistic, so you must control how forgiving it is. Here's the flow on every incoming prompt. First, embed the prompt with a model like text embedding 3 small. Second, run a nearest neighbor search against your store of past prompt vectors using cosine similarity. Third, check the top match against a similarity threshold. If it clears the bar, that's a cache hit. Return the stored completion and you're done. If nothing clears the bar, it's a miss. Call the chat model. Then write the new prompt embedding and its answer back into the store so the next similar question hits. The embedding call is cheap and fast compared to a full chat completion, which is what makes this worthwhile. A practical wiring on Azure looks like this. Your application calls Azure OpenAI for embeddings using the embedding deployment. Those vectors go into a vector store. Azure AI Search with a vector index works well, or Redis with vector similarity if you want sub-millisecond reads. On a hit, you return the cached completion straight from the store. On a miss, you call the Azure OpenAI chat deployment. Then write the prompt vector and the answer back. Keep the embedding model and the chat model as separate deployments so you can scale and version them independently. This keeps the cache layer cleanly in front of your most expensive call. Here's the core in Python. We embed the prompt, search the vector store, and branch on the best score. Note the threshold comparison. That single number decides everything. Cosine similarity runs from -1 to 1, where 1 is identical meaning. For paraphrase detection, a threshold around 0.92 to 0.95 is a reasonable starting point, but you must tune it against your own data. Too low and you serve wrong answers. Too high and you barely cache anything. 3 knobs dominate. First, the similarity threshold. This is your precision versus hit rate dial, and the right value depends on your embedding model and domain, so measure it. Second, time to live. Set an expiry on entries, because answers about prices, inventory, or anything time sensitive go stale fast. Third, the cache key scope. Raw prompt text alone is rarely enough. Fold in things that change the answer, like the system prompt version, the model name, the user's language, and any tenant or permission context. If two users should see different answers, they must never share a cache entry. Now the traps. First, false hits. Two prompts can sit just above your threshold yet expect different answers, like asking for revenue in 2023 versus 2024. Numbers and named entities embed very closely, so consider extracting them and matching exactly. Second, cross-tenant leakage. If your key scope is sloppy, one customer's cached answer leaks to another. Treat that as a security bug, not a cache miss. Third, distribution drift. If you change the embedding model or its deployment, old vectors are no longer comparable, so version your index and rebuild. And remember, embedding calls and vector storage cost money too. So confirm the cache actually pays for itself before celebrating. To recap, a semantic cache embeds each prompt, finds the nearest stored vector, and serves a cached answer when similarity clears a threshold, falling back to the model on a miss. The threshold, the time to live, and the key scope are the settings that make or break it, and false hits, tenant leakage, and embedding drift are the failure modes to design against. Your one concrete action: before tuning anything, log live prompts, replay them through your cache, and measure hit rate and false hit rate at several thresholds. Let data pick the number. And since model names, pricing, and vector features change often, check the current Azure docs for the latest embedding models and Azure AI Search vector limits. If this helped, do me a favor, hit the like button, subscribe, and tap the bell so you don't miss the next one. See you in the next video.